This is section 10.1, Conics and Calculus. In this chapter, we're going to be reviewing several topics that you learned about in pre-calculus: conic sections, that's circle, parabola, ellipse, and hyperbola; parametric equations, that's where you have a parameter t or sometimes theta, which is a third variable, the independent variable for both x and y; and polar coordinates. So this should be review, a lot of it, and then we'll sprinkle in a little bit of calculus as we go. But to start with, a lot of this will be pre-calculus review. So if you look at the figure 10.1, a conic section can be described using a double napped cone, which is what that is: two cones that are the same size and shape with their tips together and their bases parallel to each other. And if you take a plane and intersect it with the double napped cone, the places where the cone and the plane intersect creates a conic section. So if the plane being held is parallel to the base of a cone, then you get a circle. And of course, the closer that plane is to the tip of the cone, the smaller the circle, and vice versa. If you go away from the tip, the circle gets only bigger and bigger. And in fact, these cones are really supposed to be infinite in size, so we can only draw a finite size there, so that's why it looks like it's finite, but it's actually infinite in size. If you tilt the plane slightly away from being parallel to the base, you'll get an ellipse. And again, you get different size ellipses the closer you are to that common point. If you tilt it just far enough so that the plane is parallel to the side of the cone, then you get a parabola. You tip it a little bit further, and it actually for the first time touches both cones, and you get a hyperbola, and it's two branches. There are degenerate forms for these. If your plane happens to cross through the common tips of the cones, then you get what's called a degenerate conic. If that plane is parallel to the base, you get a degenerate circle, and it will be just one point. Let me write that down. I can't spell. Well, I can, but not today. Degenerate conics. Degenerate circle is a single point. Degenerate ellipse is also a point. A degenerate parabola is a line. So the plane goes right along the edge of the cone, crosses through the common tip and along the edge of the other cone. And then the degenerate hyperbola is two intersecting lines. You might notice as the plane gets closer and closer to the common tip of the two cones, the two branches, their vertices, get closer and closer to each other. And of course, as soon as you cross through and are at the place where you've got the tip as a point in the plane, then you get two lines, two intersecting lines. You will encounter these occasionally, these degenerate forms, but not all that often. But I thought I should mention them to you in case that is something that you encounter. You'll know what you're dealing with. All right. So the method that we're going to go about studying these is, as the Greeks did, defining the the cone and plane intersection as a conic. We can do it that way. We could also define them algebraically, where every conic is a quadratic equation when in an algebraic sense considered. Of course, the first three terms are quadratic because the sum of the exponents is 2, or every one of those. So those are three quadratic terms. And then, of course, we allow for a linear term in x, a linear term in y. That's all the linear terms that are possible. And then a constant. And any conic is going to fall into an equation that can be written in this form. You may not see it in this form, but it can be written in this form if it is indeed a conic section. A, B, C, D, E, and F are just real numbers. Some of them can be 0. In fact, for a lot of what we will talk about, a lot of the ones we see, B will be 0. There will not be an XY term in our equations. For the most part, that's going to be the case. There are a couple of exceptions, but by and large, we're going to stick with the easier ones where XY terms are not visible. Okay, so then that's another way to do it, and we will talk about that particular way as well. But there's a third approach which defines each of the conics as a locus or a collection of points that satisfy a certain geometric property. And that's the one I want to start with. For example, a circle is defined as a set of all points in the xy plane such that their coordinates xy are equidistant from a fixed point hk. So here's the xy plane, and we have some point hk which will serve as the center of the circle. And in fact, hk, get used to that, that's very frequently used to describe the coordinates of a special point on the figure. So for the 4 conic sections, hk plays a very big role, as you'll see. I'm going to try to draw what this would look like. It's supposed to be the set of all points that are the same distance from that one point. And so I'm going to try to draw a perfect circle. I'm pretty sure I'm failing, but oh well. Pretend like that's a really well-drawn circle, perfect in every way. No, it's not, but pretend with me. Okay, well, wow, pretty bad. Nevertheless, so for any point xy that is on the circle, every one of those points xy, wherever they might be, are all the same distance from the center hk. And of course we call that distance between those two r, the radius. And to get to the equation of such a circle, we could use the definition I just mentioned and say, well, that radius, that distance, is the distance between those 2 points. So I'll use the distance formula, and that's going to be x sub 2 minus x sub 1 squared, this is the distance formula, plus y sub 2 minus y sub 1 squared. And if we square both sides of that equation and move or switch the sides of the equation as well as squaring both sides, we will get this equation, which is the generic form of the equation of a circle centered at hk with a radius length of r. Okay. So this is the standard form for the equation of a circle, and you need to know this standard form for lots of reasons. And the standard form of all of them is that when you have this in standard form, you can easily identify parts of the figure that you're going to be drawing and very quickly draw a sketch of it. For example, if I asked you to graph the circle with this equation, you would be able to just look at that and tell me the coordinates of the center. Notice the formula is x minus h and x and y minus k, which means you're going to say the opposite of what you see. So the center's coordinates are +1, -3. And the radius of that circle is the square root of 25, 5. And so you could very quickly draw this circle, almost said parabola. Whew, getting ahead of myself. Let me put some marks here on the axes so that we have kind of a common starting point as to just how far one unit is. Okay, I think that's enough. So we could plot the center at 1, -3, and then this is something I didn't do before, which I probably would have had a lot more success drawing a really good circle, is I need to go 5 in every direction. The easiest direction to count off is up, down, left, and right. So I'm going to go up 1, 2, 3, 4, 5. To the right, 1, 2, 3, 4, 5. To the left, 1, 2, 3, 4, 5. And down, 1, 2, 3, 4, 5. 1, 2, 3, 4, yeah, okay. And then do your best to draw a circle. Keep in mind, circles are not straight things, so don't make anything that looks straight in between these points. It should look like a curve. I'm kind of leaving a little bit of gap there so you can see where that point is, at least until I get more of it drawn. Then I'll fill it back in. But that's kind of a okay graph of this circle. And when you finish graphing, I should be able to see the 4 major points that you plotted from the center 5 units away each. Now, obviously, this is not the drawing of a perfect circle. To do that, you'd need an instrument like a compass to make it look really good. I'm not so very concerned with perfection here. As long as I can tell what you were trying to do and you did your best, that's fine. Just try not to make a circle look like a diamond. That is not good. Don't do that. Try to make it look curved. All right. Now, onto the parabola. A parabola is the set of all points, x, y, that are equidistant from a fixed line called the directrix. So here's a fixed line. And by the way, whenever we say a fixed line or in this setting, we could have a line that is non-vertical and non-horizontal. That's perfectly possible. We are not going to deal with those in this section. But let me talk about it in sort of that generic way first, and then we'll talk about specifically ours. So this is supposed to be a vertical line. It doesn't look very straight up and down, but please pretend with me. Or the directrix might be a horizontal line. And of course, the third type, the type we're not going to deal with, is if the line is something other than horizontal or vertical. And again, we're pretending like the first one I drew over there is vertical. It doesn't look very good, but oh well, I'll live with it. Okay, so there's that point, or that line called the directrix, and then there's a fixed point, not on the directrix, called the focus. I'm going to label that with capital F. The vertical directrix can have the focus on either side. I happen to draw the focus on the right side this time. It could have been on either side, and it doesn't have to be a prescribed distance, short or long. It can be anywhere, just not on the line itself. And so, and then this one up here, which again, we're not going to encounter that type that I'm drawing at the far right, but I want you to kind of see generically what we're talking about. I may do that a little bit with some of the other figures, but not seriously, because basically everything we deal with has to have pieces and parts and components of them that are horizontal and vertical only. For our purposes, that makes it way easier. And that's why we won't see an XY term, because that's one of the roles of the XY term, is to rotate a graph. This one on the far right, say it was horizontal and it got rotated about 45 degrees counterclockwise, and that's what you get. And that an XY term would not be zero then in that situation. Okay, so we're going to find all the points that are equidistant from the focus and the directrix. Say, for example, this point right here. If I were to measure the distance from the focus to that point, and then measure the distance from the directrix to that point. And by the way, when you measure distance from a line to something, it's always going to be held at a perpendicular to the line. And those two distances would be the same. And so we're looking for the set of all such points. A good one right here is the one that's exactly halfway between the focus and the directrix, and that one actually has a special name. And before I finish, maybe you can remember what that is. And maybe another one right here, let's say that works. And then the whole set of points would be all of these. Now, I'm not claiming that this is a perfect drawing. Please don't mistake me. If you want a perfect drawing, oops, that looks too straight. If you want a perfect drawing, you're probably going to have an artist or a machine do it. You're not going to get it from me. I'm not very good at drawing things to be perfect looking. I do my best, but I usually fail. Don't have perfection. Okay, anyway, that's sort of the shape of a parabola. All right, so this one right here with the horizontal directrix would look something like this. Okay, and those are ones that you've seen before in previous classes. This one here is going to look weird because you've never seen one with a directrix that is not vertical nor is it horizontal. And it looks like that, kind of going off at a crazy angle like that. All right, like I said, the first two drawings are more in line with what we're used to seeing. And in fact, the middle one is the one that you've probably seen the most of, thinking all the way back to high school when you first started with parabolas. Weren't they always something of the form y equals ax squared plus bx plus c? Remember those? Well, of course, that is where x is squared and y is not squared. And that's one of the hallmarks, by the way, of a parabola, is that there is only one squared variable. The other one is not squared. And because of what you studied, you know that this one is a function because it passes the vertical line test, right? So it's a function and it's got x squared. Go with what you know. That is something you know for sure, that you've seen parabolas with y equals x squared in them, and they are always functions. They pass the vertical line test. On the other hand, the first one on the far left does not pass the vertical line test. It is not a function. Oops, well, that's supposed to be vertical. Let me try that again. Well, so the directrix was supposed to be vertical too, but oh well. Man, that's awful. I'll try one more time. Okay, a little bit better. Anyway, it does not pass the vertical line test, and what this one looks like is x equals a y squared plus by plus c. And that means that x is a function of y. Notice again, only one variable is squared in this equation. In this one, it's the y that's squared, x is not squared. In the first one, the one in the middle, I guess I should say, the x was squared and the y was not. And when x is a function of y, it is not going to pass the vertical line test necessarily. In this one, it won't. Okay? All right, so the coordinates of the focus are important. There'll be some xy. Well, wait, that's going to be reserved for something else. Well, it'll be just a point. Let's just say that. It'll have coordinates. Any point on the parabola is going to be, and this is why I had to back off the other, is going to be some ordered pair xy that makes the distance from the focus to that point. So let's kind of draw that in. The distance from the focus to that point and the distance from the directrix to that point exactly the same. And that's what makes it a parabola. And anybody remember what this point here is called that's at the midpoint between the focus and the directrix? Yeah, it's the vertex. And the vertex is always that point that's midway between the focus and the directrix. So there's the vertex there, and there's the vertex there. Halfway between the directrix and the focus is the vertex. Okay, and that is what's going to get the special coordinate name HK. So in this, the vertex is HK. Okay. Oh, we were talking about how to recognize the equation of a figure. For a parabola, either x is squared or y is squared, but not both. We'll come back to the circle and talk about it, but if you think about it, if I were to have done the squaring up there with this original equation, this one right here, I would have had x squared and some stuff and y squared and some stuff equals, well, eventually we could subtract 25 from both sides and get 0. So what tells you it's a circle is if the coefficients of x squared and y squared are the same number. In this case, it looks like they would both have a coefficient of 1. There is an x squared and a y squared in the equation of a circle, and their coefficients are equal. Whereas for a parabola, there is only one squared variable. The other variable will not be squared. Okay. Now, we could derive the equation of the parabola using the distance formula from focus to xy and then from xy to the line. And we could go through all that, but I'm not going to do that in this course. That's something I generally talk about more in pre-calculus. So let me just tell you what the equations are in standard form. So for the parabola that opens upward or downward, that is, its directrix is a horizontal line, which would be y equals some number. I don't want to call it k. I don't want to call it c because it's not necessarily. It's y equals some number. I'll just put a pound sign standing for a number. It's going to be some number. Okay? That's awfully messy. Let me try that one more time. Y is going to be equal to some number if it's the equation of a horizontal line. And in that case, the equation looks like this. The standard form for the equation of a parabola with a horizontal directrix will be x minus h quantity squared is equal to 4 times p times the quantity y minus k. And so that's the equation, the standard form of the equation of a parabola as described above. And what that means is that it will either open downward or upward. If the focus had been on the other side of the line, that parabola would have opened upward. And those are the two possibilities for this equation. Let me talk about P. Well, first let me write this down because I already said it, but I think it'd be worth repeating. The vertex, of course, is, as I said earlier, HK. P is the directed distance and this is a generalized statement which is true for all parabolas. P is the directed distance from the vertex to the focus. Now, if you went through pre-calculus here at TCC, you probably recall that the equation, they used a different letter. Instead of P, I believe they used C. So if I sometimes slip and say C for that, it's because I'm thinking of the pre-calculus version. It doesn't really matter, what letter of the alphabet is used there, but in this book, I'll try to stay with P because it's a little bit more consistent. Okay, so over here with the directrix that is vertical, and that's going to be an equation of the form x equals a number. When you have a vertical line as a directrix, then that equation will be y minus k squared equals 4p times the quantity x minus h. Notice that the x coordinate is with x and the y coordinate is with y inside of those parentheses. Okay? And as it says right above there, the vertex is hk, and as I said to the right, p is the directed distance from the vertex to the focus. Okay, so you may notice in Theorem 10.1, where they've given all that, they have all kinds of formulas in there to find the equation of the directrix and the coordinates of the focus. And that's fine if you want to memorize those. It's not the way I tend to work on these, so I'll show you what I do and what I think through, and if you like that, you may do it, of course. If you prefer to do the textbook way, that's certainly fine as well. You should get the right answer. It just means you have more to memorize. Okay, anyway, so here, let's do our first example. I'm going to start with y equals 1/2 minus x. And if I stopped right there, of course, that would be the equation of a line, right? Because there's nothing quadratic in this. It's the next term that makes this a quadratic relationship, which means it is one of the conic sections, minus 1/2 x squared. And I know what this one is because there's only one squared variable in the equation, x. Y is not squared, and so this is a parabola for sure. Okay? Now, what we're going to do now is to try to get it in the standard form where x is the square thing. That's going to be this one that was in the middle before. And one of the major tools we use, even for the circle, which I didn't show you an example of that, but even with a circle, to get that binomial squared, you're going to have to remember how to complete the square, which is an algebraic thing that you learned way, way back in college algebra, and maybe before that in high school. But you're going to have to complete the square. Big topic in the conic sections. So let's talk about how to do that. So one of the things I'm going to try to do is I want the x squared term to have a positive coefficient. So I'm going to add 1/2 x squared to both sides. And in the end, you're going to see one of the things I'm going to say is I want all of the squared variable stuff on one side and everything that's not that variable or is a constant, I really want on the other side. So that means I'm going to have to add x to both sides to have all the x things on that side. And then I'm going to have to subtract y from both sides to move it over to the other side. And the 1/2 that's already there is positive. Okay, So to complete the square, the first thing you have to have is the coefficient of your squared variable must be 1. Must be 1. And so I'm going to factor the 1/2 off of the x squared term so that inside of the parentheses, the coefficient of x squared is 1. I have to do the same thing to x. I have to factor off a 1/2. So if I factor off a half, that's going to leave 2x inside. Then leave a little bit of space there for completing the square. All right, so once you have the coefficient of x squared in this problem 1, you look at the coefficient of x inside those parentheses, find half of that number, so half of 2 is 1, then square the result. So half of 2 is 1, the square of 1 is 1. So I'm going to add 1. And of course this is a new thing, and I've now messed up the equality of this equation by adding 1 inside the parentheses there. I've messed that up. What I can do to fix that is to add the same thing on the other side. What you have to be aware of is that if you distributed that 1/2 back through, what we really added to the left-hand side is 1/2 times 1 to the left-hand side. So we have to add 1/2 times 1 to the other side as well. Okay? And I know you could do 1/2 times 1 in your head. Again, for note-taking purposes, I sometimes write more than you need to see to make sure you understand where things came from. Okay, then to factor that trinomial that you just completed, you'll take the square root of the first term, which is x, the sine of the middle term, which is plus, and the square root of the third term, which is 1, close the parentheses and put a square on that. And you've just completed the square and factored the trinomial. Collecting like terms over here, this will be negative y plus 1. Okay, so if you look at that starred equation up at the top in the middle, the x minus h quantity squared is not allowed to have a number in front of it. It has to be an understood one. So the 1/2 that's right now there, I need to get rid of that. So I'm going to multiply both sides of the equation by 2. I'll multiply the left side by 2. I get x plus 1 quantity squared. And on the right side, I'll get negative 2y plus 2. I distributed that 2. So the next part of getting this into standard form, if you notice on the right side of that equation up above, the one that has a star, the y inside parentheses has to have a coefficient of 1. And so that's a necessary part of this. So I'm going to factor off that negative 2 on the right side. And factoring that off, I get y minus 1. And that is now in standard form. And we can identify the coordinates of the vertex easily. That's going to be, remember it's the opposite of what you see, negative 1, comma 1, x then y. And you'll want to write this down that 4p is, in this problem, equal to negative 2, so that you can solve for p, which is negative 1/2. Okay? So, let's, now that we have this in standard form and we've identified those two pieces, let's draw a graph. And I'll show you how the P is used in graphing and how we can make a pretty decent graph with the information we have. By the way, with P being small, very close to 0, I'm going to need pretty big marks on the graph. All right, so we know that the vertex is at negative 1, 1. So go ahead and plot that point. And you can label it with a V if you want to. It keeps me maybe from making mistakes. Okay, so the focus, according to our definition of what P is, it's the, if you recall, it's the directed distance from the vertex to the focus. Since P is negative, that means we're either moving to the left or down. Those are the negative directions. Negative Y's are in the down direction, negative X's are in the left direction. So it's one of those two. The way to know which one of those it is recall the parabola that has an x squared in it is the one you've dealt with. Your whole high school and college career so far has been mostly with x squared as your variable that's squared in a parabola. So remember, this is going to be a function, okay? And since it's a function, that means that we're going to have to go down 1/2. So that's where the focus is. Okay. Now, because the vertex is the midpoint between the focus and the directrix, what you can do is you can go 1/2 in the other direction to here, and then draw a line. And if you think of the vertex and focus as being on a line segment, this line I'm drawing should be perpendicular to that. By the way, the line that goes through the vertex and the focus is called the line of symmetry. So if they were to ask you to locate the directrix and tell you what its equation is, so what is the directrix for this one? Since it's a horizontal line, it will have the equation y equals a number. And of course, if you remember where the vertex was, it was at positive 1. We went up 1/2, so it's at y equals 3/2. And then you might also be asked for the coordinates of the focus. And if you think about where we started at negative 1, 1, we moved down 1/2, which meant that we would be still at negative 1 for the x coordinate, but only at positive 1/2 for the y coordinate. And again, if you wanted to go and look up the formulas in that theorem 10.1 and use those, you should get the right answer. It won't matter. I like to do it visually, like we just talked through. I think that's a better way to envision it. But if you want to use those formulas, be my guest. Okay. Now, there are 2 points on the parabola that I want you to graph and graph with confidence. And they are these. And I'm going to have to develop the idea first. So just stick with me for a second. The distance from the vertex to the focus is a distance of p. Now I'm thinking of absolute value distance. And the distance from the vertex to the focus is also p. So obviously that's a total of 2p. If I were to move 2p, and p is 1/2, I were to move twice p, which would be 1, to the right. So going parallel to the directrix. If I move to the right 2p, which is 1, and from the focus left 1, so I'm moving parallel to the directrix to do that, those 2 points are definitely on this parabola because they're 2p away, because you move parallel, they're 2p away from the directrix, and they're 2p away from the focus. So that is a good way to graph. And in fact, the total distance between those last 2 red dots I made is a total distance of 4p. And look at our equation. That's related to the equation. So that may help you with remembering how to do this. Anyway, I'm not going to draw those things I just did in that lime greeny color all the time. I wanted to explain it though. So using the vertex and those 2 points we just plotted, we will do our best to draw a parabola. realizing, of course, it's not perfect, but it is curved. Please don't draw something that looks straight. There we go. And there's our parabola. A silly thing that I have said to classes before is that if P is positive and it's a function, that means it opens upward. And if P is negative and it's a function, that means it opens downward. And so if P is positive, it's kind of like having a good day, you're happy and all that, and you have a little smile on your face. But if P is negative, which is kind of a downer, it's kind of negative and bad, you have a little frown on your face. I don't know if that helps you, but it's silly. But nevertheless, some people find that to be something they can remember. Now, as far as the P being positive, for the one where y is squared, that's going to open to the right when P is positive and to the left when P is negative. Okay? Because if you'll look, every vertex that, every focus that you plot is kind of inside of the parabola. If the parabola were a cup, the focus would be inside of that cup. Okay? And the directrix is outside of it and never intersects. So I'm just going to draw a couple of them, not all of them, because it's going to make this picture look kind of crowded. But that's how the pictures would look. Well, I guess I can go and draw these. This guy needs a mustache anyway, and this one needs a tie. All right, so I went ahead and drew them all anyway. I guess that's okay. All right, so that's going to be how you'll know which way to open the parabola. All right, so let's move on to example 2, part A. This is a pretty standard way to ask the question, is to be given the equation in this form, the one we started with at the beginning, the ax squared plus bxy plus cy squared, etc. form. Maybe not in absolutely that order, but in other words, you see that they have not completed the square for us. We're going to have to do that. So when the equation is given in this form, completing the square is usually a pretty big part of finishing the problem. So as I said earlier, since y is the thing that's squared, I want all of the y things on one side of the equation and all the non-y things on the other side. So I'm going to subtract 8x and subtract 25. Then I'm going to complete the square on y. Since the coefficient of y squared is already 1, I don't need to do any heroics of factoring out something. I'll just look at the coefficient of y, which is 6, take half of it, which is 3, square that. Square of 3 is 9, and I'm going to add 9 to the left-hand side to complete the square. To keep the equation in balance, I'll have to add 9 to the other side as well. Okay, so factoring, I'll get y plus 3 squared, and combining like terms on the right side, I'll get negative 8x minus 16. Then, recalling that the variable that's not squared needs to be such that it has a coefficient of 1 inside parentheses, I'm going to need to factor off that negative 8, leaving x plus 2. Okay, so we now know that the vertex is at what? I hope you said negative 2, negative 3, and weren't simply reading left to right and accidentally said negative 3, negative 2, which is false. The x-coordinate is with x in the equation, and the y-coordinate is with y. Okay, so we found the vertex. To find the focus in Directrix, I know it says sketch the graph last, but this is the way I think through this, and I think it usually works pretty well. At least this is the way my mind grasps it. Is, you know, once I see a picture, I'm like, oh yeah, I get it. And everything becomes clear. All right, so let me put a few points on the axes. I didn't mean points, I meant tick marks. Okay, so our vertex is at -2, -3. There's the vertex. I'll set for p equal to -8 and solve for p. So p is -2. Remember, when p is negative, that means we're either moving left or right. Because this is a y squared, it's not a function, which means it will open left or right. If p is negative, that means it will open to the left. So I'm going to move to the left 2, and that's the focus right there. And since I have to find the coordinates of the focus, right there when I'm plotting it, I'm going to just count up and see where it is. It's at -1, 2, 3, 4, -4, -3. Okay, then the directrix is going to be 2, but in the opposite direction. Since I move left to get to the focus, I'm going to move right 2 to get to the directrix. And the directrix ends up being the y-axis. And of course that means that the directrix, since it's a vertical line, has the equation x equals a number, which in this case is 0. And that's another thing we were supposed to find. So actually, I think we now found everything that the question asks us for, except for the graph. So we just need to finish the graph. Okay, so I'm going to think of the vertex as a point on my curve. So I'm going to make that red so that's on my curve. I'm going to think about the absolute value of p, which is 2, and double it. Doubling 2 gives me 4. I'm going to start at the focus and go parallel to the directrix. So up 1, 2, 3, 4, and down 1, 2, 3, 4 from the focus. Okay, make sure you're going from the focus. And those 3 red dots are points that are on my parabola. So I'm going to do my best to draw a parabola that passes through those 3 points. And it should be a curve, not a line, so be careful as you draw it. So let's look at example 2, part B. Now this one is sort of a reversal of what we just did. Given an equation, we had to find the vertex, focus, and directrix and graph. Now, given pieces of that information about the graph, we're going to be asked to find the equation. So the vertex is given to be at -2, 1. Okay, so immediately when I get information like that, my gut reaction is I should probably start graphing things as we go. So put a few marks on each axis. Hopefully I'll have plenty and not need to draw more than I just drew. We'll see. Okay, so I'm going to plot the vertex at -2, 1. And the focus is said to be at -2, -1. So -2, -1 is the focus. Well, remember P is the directed distance from the vertex to the focus. And since we're going from the vertex down, P will be negative, and the distance we move is 2 units. So P is -2. Now, the thing that I said earlier about the focus is always inside of the cup, what that implies is that our graph will have to open downward. That's the only way that focal point will be inside of the parabola. If we'd gone up, left, or right, that would not have happened. So, since it's one that opens that way, that means it's a function, and we're looking for an x² kind of problem, not a y² kind of problem. So, the equation will be x minus h. X minus -2 is the same thing as x plus 2 squared equals 4 times p, 4p, times y minus k, which is 1 in this problem. And so our equation that we would want to stop with and say we're done is x plus 2 quantity squared equals -8 times y minus 1. If you wanted to get a better graph, you could certainly do all of that. My purpose in drawing that over to the left side was to determine whether it was an x² or a y² kind of parabola. So that's not supposed to be a really good picture at all. It's just to get my thinking straight. Now, those 2 points that we graphed up here, and any of the other ones we could have pointed out, but this point and this point are the endpoints of the segment on a parabola called the lattice rectum. And those are really easy points to find if you know what P is, therefore you know what 2P would be. And you might notice if I were to draw that segment in, drawing the lattice rectum, the focus is the midpoint of the lattice rectum. So that's a good pair of points to know. Now, one of the things that parabolas is used for, kind of a physics setting, is a parabola has a nice reflective property. It's a physics term, reflective, when the tangent line at any point on the surface makes equal angles with an incoming ray and the resulting outgoing ray. So the angle corresponds to the incoming ray is called the angle of incidence, and the angle corresponding to the outgoing ray is the angle of reflection. One example of a reflective surface is a flat mirror. Another, and this is where we're getting into the parabola, another type of reflective surface is that formed by revolving a parabola about its axis. If you've ever seen a light bulb, a flashlight, and seen the bulb inside, behind it is this reflective surface, and that reflective surface has the shape of a parabola that's been revolved around the axis of symmetry to create that paraboloid kind of shape behind the light source. And if you look at figure 10.6, that light source is going to be the focus, and all rays that go out from that light source hit the parabola and shoot the angle at an angle parallel to the axis of symmetry for the parabola, and points all of those light beams straight out to the right if you're looking at figure 10.6. So no matter where the light hits the parabola surface, the light will be shot straight out, and that's what makes a flashlight work so well, is you have that focused beam. Another thing that happens, like if you have a dish satellite, it's the same idea, except for this time all of the signals are coming in towards that parabolic dish. They hit that and are going to bounce straight to the focus. So any wave that hits that parabolic surface is going to shoot the ray to the focus. And that's where you see that little receiver. I'm sure you've seen those before where, you know, here's your dish and then there's a little thing out here that's a receiver, like a box or something, and that's at the focus. Okay, so if you have a dish satellite, that's what that little box out there is doing, is collecting all of the rays from the source so you can see your TV show. Alright, so the next figure we're going to talk about is the ellipse. An ellipse, there are going to be two focal points instead of one focus, so two foci. This could be focus 1 and focus 2. And again, you're going to see that those are on purpose horizontally aligned or vertically aligned, like that. They can be at other angles, like they could be something like this, and get an ellipse that's going to look maybe like this, sort of. We're not going to deal with those in this course. So anyway, every point that's on the ellipse, let's say this point right here, has coordinates x, y, and the thing that makes this an ellipse is that the distance from one focus to any point, call that distance 1, and the distance from that point to the other focus, let's call that distance 2. The sum of those two distances is constant. Is equal to some constant. So for every single point on that ellipse, the sum of those two distances is the same number. And so that creates an elliptical shape. So I'm going to move down here and redraw that so that I don't have as many things to label. There's a lot of labeling here, so I don't want to put too much on it. So here would be the set of all points. Whoops. Well, the problem with my drawing is that it's supposed to be such that it has a horizontal line of symmetry through the foci and a vertical line of symmetry through the center. So, well, my picture is not very good looking, but maybe you can live with it. All right, so speaking of the center is the point midway between the two foci, and we're going to say that its coordinates are that special named point HK. Just like it was the center for the circle, HK is going to give us the coordinates of the center of an ellipse. Right, so we're going to label some distances here. Let's see. We're going to call the distance from the center along the longer direction. I didn't say this before, but the ellipse is longer in the direction that the foci and center lie on. That's called the major axis of the ellipse. And so this is the major axis, goes through those 3 points, the circle, the center and the two foci. The major axis goes through those. And the distance from the center to the edge of the ellipse, we're going to label that A. And by the way, another 2 points that are on that line are the two vertices. This is a vertex, and this is a vertex. So those 5 major points, the two vertices, the two foci, and the center are always collinear for an ellipse. And the distance from the center to the vertex is longer than the perpendicular distance to the ellipse. And speaking of that, we're going to call that distance from the let's say the top of the ellipse to the center in this picture, that's going to be B. And then the distance from the center to a focus, we're going to call that C. Right? And so if I were to draw a segment that is C long here, and perpendicular to it, something that's B long here, that's B, and that's C. The segment that's A units long actually always fits just perfectly to make that a right triangle. And unlike the equation you're used to for the Pythagorean theorem here, this is going to be B squared leg squared plus C squared, that's leg squared, equals hypotenuse squared. You probably memorized that C squared is equal to A squared plus B squared. That doesn't work with the ellipse. You got to reimagine that. I do want to solve this for C squared, and the reason I want to solve for C squared is that a lot of times we're asked to find the focal length, the distance from the center to the focus, or we're asked to find the coordinates of the focus. And in order to do that, we'll need to know how long C is. So you'll use this equation for an ellipse to find the focal length called C. All right. Now, if I go over to this picture over here, the same things happen over here. So let me just draw a quick picture. Well, that's really bad. Oh well. This time, the vertices are the points at the top and the bottom. Okay. And the center, of course, is midway between the foci, also midway between the vertices. That's the center. And again, all 5 of those points are collinear. If we move from the center to a focus, that's distance C. If we move from the center to the left edge, that looks horrible. Let me try that again. That's going to be B. And the distance from the center to a vertex is A. And the same triangular relationship will hold that C squared is equal to A squared minus B squared. That's not because the major axis is horizontal. It also happens to be true when its major axis is vertical, like the picture on the right, and even true when the major axis is not horizontal or vertical, like that picture way over there to the right. Okay. So, the points, by the way, that are here and here, segment perpendicular to the major axis. The segment I just drew is called the minor axis because it's shorter than the major axis. And there's supposed to be symmetry, so this picture over here to the right looks awful. But the one on the left is not too bad. That's called the minor axis. And those 2 white dots that I put on there, I'll put them over here as well, don't have a special, well, they do have a special name, it's just you don't need to memorize it because it's long and terrible. Those points are called the endpoints of the minor axis. And they're not called vertices. That's what I'm trying to point out, is they don't have the special name vertex. The vertices are on the ends of the major axis. And the endpoints of the minor axis, they have no special name other than what I just said. Endpoints of the minor axis. All right. So, there are 2 equations that are possible for this. For this one, where the major axis is horizontal, it's going to be x minus h quantity squared over a squared plus y minus k squared squared over b squared equals 1. So a couple of things I want to point out here. Notice a squared and b squared will be things you can identify easily from the equation. And this equation down here will be used if you want to find out what c is. Again, the center has coordinates hk. And what I like to call the value of a in this particular problem, I like to call that the x radius, because it's how far you're going in the x direction from the center to get to the vertex. And b in this problem is what I like to call the y radius, because in this picture it's the distance I'm moving from the center in the y direction to get to the endpoints of the minor axis. And by the way, since A is the major, or gives us half of the major axis, and B gives us half of the minor axis, A is always bigger than B. Okay? Now, the equation when the major axis is vertical is y minus k squared over a squared plus x minus h squared over b squared equals 1. And I just noticed in the book they have these two fractions that are added to equal 1 opposite order. They put the x fraction first, the y fraction second, which isn't really a bad idea, because when looking for the coordinates of the center, you want to kind of rely on the fact you can read right to left, left to right, and you want to do the h first and then the k second. And the order I have it in, you'll have to read from right to left to get that. But the center is still hk. In this problem, a is the y radius and b is the x radius. And you can tell that this is moving further in the y direction because a is always bigger. The number a is underneath the y, so the y radius is a longer number than a longer distance to plot than the b will be, in this case, the x-axis, x radius. All right, so for all of that, I don't like these two equations as well as I like the one I want you to work with, which is, this is one equation fits both situations. That is to say, x minus h quantity squared over the x radius squared. Whether that's the shorter or longer distance doesn't matter. It's still how far you're going to move in the x direction. Plus y minus k squared over the y radius squared equals 1. Okay? So that's the equation I would like for you to use. I think it's more useful than memorizing 2. You'll also need to memorize the one that we put a star next to over here. So those are the two things you'll need to have in your head about the ellipse. I've run out of room on this slide, so I'm going to move to the next recording.